later on. And don't forget that you have you need to submit me exercise 2.1, and the due date is by midnight on Wednesday midnight. Okay. Okay, now I'm gonna start the second part of topic 2, which we're gonna start about polygons. Polygons, the other name of shapes. So we're gonna go through some basic shapes that we are going through in this course. So what is the definition of polygons? A polygon is a closed plane figure whose sides are line segments that intersect only at the end points. And then we have some definition here, some different type of polygon over here. Oops. Here we have convex polygon. We have convex polygon, where convex polygon is a polygon whose the angle measures are between 0 and 180 degrees. And we have concave polygon, where it's a polygon that has one or more interior angles greater than 180 degrees. So these angles are called reflex angles. Okay, reflex angle is any angle that are greater than 180 degrees. So to see the example, so we have convex and concave. So this is this is some type of example of convex polygon here, and you can see that this is concave polygon. Whenever you saw a shape and it have one angle which is more than 180, for example, for this blue, okay, this blue shape here have 180 degrees over here, and for the red one here, the 180 degrees is this part. Okay, so whenever you have at least one reflex angle in the shape, then we call it a concave polygon. Okay, so this one is not polygon because this one is not a straight line. It's not a closed closed shape, and this one is like just a doesn't have a straight line as well. So you need to identify which one is convex, which one is concave polygon, and which one is not polygons. Okay, so in this table, there are some polygons and the number of sides for each of them. For each of the polygon, we have triangle, number of sides is 3, quadrilateral 4. So we didn't see it as a rectangle or square. We see it as in general as the general term is quadrilateral. Then we have pentagon, 5 sides. 6 sides is hexagon, heptagon, octagon, nonagon, and decagon. Then it can go on, but it's if you only know up to this, it'll be good enough. Okay. Then let's go through about a diagonal. A diagonal of a polygon is a line segment that joins two non-consecutive vertices. So for example, triangle, there are 3 sides, so there are three vertices for triangle. So we need to look when we can draw a line that connect the vertices, then we see that is the diagonal of the polygon. So let's look for an example here. Okay, this is triangle, number of sides 3. So RST is the 3 vertices of triangle, but when we connect between the 2 vertices, we just connect the line of the triangle. So there are no there's no diagonals for triangles. But for quadrilateral, for example, this shape MNOP, we can connect vertices M to P and O to N. But we cannot connect M to O because it's going to be the line of the polygon, the side of the polygon. So quadrilateral have 4 sides and 2 number of diagonals. For pentagons, we have 5 sides and we have 5 diagonals line. And then for hexagon, we have 6 sides and we have 9 diagonals. The number of diagonals is 9. So you can see here, we already show here up until hexagon. You can see from heptagon, they have 14 diagonals, octagon 20 diagonals, nonagon has 27 diagonals, and decagon has 35 diagonals. So it can be listed if the number of sides of the polygon is small, but as the number of sides increase, it becomes more difficult to count all the diagonals. Therefore, there comes the following theorem. So from this theorem, we know that the total number of diagonals D in a polygon of n side is given by the formula D equals to n times n minus 3 over 2. Okay, so for example, here we have decagon. Decagon have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 sides. So n is equal to 10. We put the value 10 in n over here, and then we will get the value of d is equal to 35. Okay, so this is, you can use this formula to calculate the number of diagonals. Rather than you draw, if you draw like this, it will be hard for you to count number of diagonals over here. I think you can try halfway, but then towards the end, you're gonna lose finding the lines already. Okay, so let's look at an example here. First, find the number of diagonals for any pentagon and the type of polygon that has 9 diagonals. So the first one, we need to find the number of diagonals for any pentagon. So that means when we say any pentagon, that means it doesn't, because when we talk about pentagon, we always imagine as a pentagon with a same length of sides. But when we say any pentagon, that means it can be not equal length for all 5 sides. And then for B, the type of polygon that has 9 diagonals. So we are given the number of diagonals as 9. So we need to see, we need to find the type of polygon. So first, pentagon has 5 sides. Thus n equals to 5. So we put the value of 5 here, and then we got D is equal to 5. So pentagon has 5 diagonals. Okay, so now the other way around, since we know that the number of diagonals is 9, then we put D is equal to 9 over here, and we try to solve it, and then we got n equal to minus 3, and n equals to negative 3, and n equals to 6. But we know that n is always a positive number. Then we took the second value of n, which is equal to 6. So when n is equal to 6, which is the polygon have 6 sides, then the polygon is a hexagon. Okay, let's go through the next theorem. The sum S of the measures of the interior angle of a polygon with n sides where n more than 2 is given by this equation. So for example, you know that the summation of the interior angles of a triangle is always 180. So we know that the number of sides is more than 2, which is 3. So we can plug in 3 over here, and then 3 minus 2 equals to 1 times 180. So we got S here equals to 180. So it's as the same like what we learned before, the knowledge that we get before. It's always equal to 180, regardless what shape, what kind of triangle. Is it with the same length or different length? Okay. Sorry. Okay, let's look for an example. Okay, find the sum of the measure of the interior angles of a polygon of n sides if n equals to 5 and n equals to 10. So when it's easy, you just take the formula here for S to find the sum of the measure of the interior angle, and you plug in n equals to 5. Then you got over here, when you n equals to 5, S equal to 540 degrees. So n equals to 5 is a pentagon. So the sum of interior angle of pentagon is 540 degrees. And then when n equals to 10, you got 1440 degrees. Okay, next. In this part, we want to find the number of sides in a polygon whose sum of the measure for its interior angle is 2160 degrees. So this time they give the value of s, and they want us to find the n. So we put s equals to 2160 degrees, and we need to find the value of n here. I think you know how to do this. It's easy. And then you will get n equals to 14. So therefore the polygon has 14 sides. Okay. Now let's look at a definition of a regular polygon. Okay, a regular polygon is a polygon that is both equilateral and equiangular. In other words, a regular polygon is a polygon where both its sides and angles are congruent, equal measure. Okay, so equilateral means having all sides of the same length, but equiangular means having all angle equal measures. Okay, and normally we put dash to indicate the congruent side, and we put the arcs indicate a congruent angle, because as you remember last time, if we deal with any diagram, if we have a one dash, we have 4 lines that have one dash, we know that all 4 lines have the same, all 4 lines are congruent or the same measure. But when we want to indicate another line which is different than the first 4, we normally put as we normally add another dash. So 2 dash for a different different measures, different length from the one before that. So as you can see, this is some of the example of regular polygon. This one is a square, same side, so equilateral, and same angle for all 4 vertices. That means it's a equiangular. Okay, equilateral and equiangular. Okay, but this one actually in this figure, it's not an example of regular polygon, because it have a equal angle. The angles are congruent, so it's equiangular, but the length is not equal, so it's not equilateral. But for this one, a pentagon is equilateral and equiangular. Okay, anyone can give me an example for a polygon that only equilateral? Anyone? I can give you a hint that it is part of quadrilateral. No.
Rhombus.
Say again? Jadi siapa yang nak try tadi? Boleh repeat balik tak? Tak dengar.
Rhombus.
Rhombus. Good job. Yeah. Kalau rhombus, it's have a equilateral, but it's not equiangular. Okay. Okay, now this corollary, find the measure I for each interior angle of a regular polygon or equiangular polygon of n side. So given that we have a regular polygon or equiangular polygon, that means something like this. Okay, of n side, we can find the measure of each interior angle as I here. So we put the value of n, we can get the value of I. So I is the value of this part. For example, for this diagram, I is the value for each angle inside this pentagon. Okay, and the sum of the measures of the 4 interior angles of a quadrilateral is 360. Okay, I think like kind of general knowledge that we have learned before. Same like the sum of the measures of the three interior angles of a triangle is 180, but for a quadrilateral is 360 degrees. And the sum of measures of the exterior angles of a polygon, any polygon. So the sum of measures of the exterior angle of any polygon, one at each vertex is 360 degrees. So, for example, this is a pentagon. We have 1, 2, 3, 4, 5 vertices. In each vertex, for example, vertex 1, they have this is the exterior angle. The exterior angles is not all the way from here to here. It's just like when we extend the line. So this is the exterior angles. The exterior angles of one is also same like if you extend this line and you have this angle here. So in this corollary here, it says that if you have all the exterior angles of any polygon, for example here a pentagon, if you add all the exterior angles, that means you add angle 1, 2, 3, 4, and 5, you will get 360 degrees. Regardless of any number of sides, that means any polygon, hexagon or whatever, when you sum all the exterior angle, you will get equal to 360 degrees. Okay, but then how to measure each exterior angle? Okay, this one is to measure exterior angle. That means what is the value of angle 1, angle 2, angle 3, angle 4, angle 5 for each one of this. So the measure E of each exterior angle of a regular polygon. That means it must be equilateral and equiangular, or polygon with equiangular only of n side is E equals to 360 degrees divided by n. So because we know that the summation is equals to 360 degrees, so obviously we want to find each one of it is by dividing with the 360 to n. Okay. So next we're going to look at a polygram. A polygram is the star-shaped figure resulted when the sides of convex polygon. So remember we have concave and convex. Convex is just a regular without having the the more than 180 degrees punya side angle tu kan. With n more than 5 are extended. So you imagine that you have a star shape and then we extend a little bit more. Okay, don't have to worry, we're going to look after this, the shape. And regular polygon resulting regular polygram, where the interior acute angles are congruent and the interior reflex angles are congruent and all sides are congruent. So there are three things that must be congruent: the interior acute angle, the interior reflex angles, and also the sides must be congruent. Okay, so this is some of the examples of regular polygram. This is pentagram. As you can see in the middle here is the shape of pentagon. But when we extend the side, we will have the star shape here, and this one we call pentagram. For this one, based on the hexagon here, shape on the middle, in the middle of the stars, and when we extend we can have the hexagram. And this one is octagram based on octagon, 1, 2, 3, 4, 5, 6, 7, 8, 8 sides. So let's look at pentagram over here. Okay, this is much more clear. The side, all the side, how many sides it will be? Because we have 5 sides over here. When we extend, we have double the sides. We will become 10 sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the 10 sides are congruent, and also all the 5 angles are also congruent. Okay, same goes for the hexagram over here. You can see in this diagram we use 2 dashes to indicate that this line have a different measure with this line. And you can see that in the octagram, we have 3 dashes here. If you can see really closely, it have 3 dashes here. So that means that this line is a different measure from hexagram and pentagram. Okay. Okay. So as for now, any question? We have polygons, several type of polygons. We have several theorems and corollary that give us some of the equation to find the summation of angle and anything. And then we have regular polygon, which are both equilateral and equiangular. And also we are introduced with the polygram with a star-shaped figure when the side of the convex polygon are extended. So I think it's quite clear up until now. Ada question tak? Tak ada kan? If you guys don't have any question, I want you to find a paper or any book, anything lah yang you can write. I want you to do exercise 2.2. There are 3 questions, 1, 2, and 3. So the first question, find the total number of diagonals for a polygon of n sides if n equals to 6, 8, and 10. Number 2, find the sum of the measure of the interior angles of a polygon of n sides if n equals to 8, 4, and 10. Number of sides for a regular polygon whose measures of each interior angle is 108, 168, 150, and 144 degrees. So I will give you 20 minutes to solve all these 3 questions. So at 2:50, I will call a name randomly from the list of people here to answer, to give me the answer for each question. Okay, so you don't have to worry. You don't have to open the your slide. You can refer here. This is the exercise, and this is all the theorems and corollary that you can find in this slide, in this topic today. So it doesn't mean that you need to use this one for this one, this one for this one, this one for this one. You just choose which one is related for this one. Okay, you can start now and try to answer this one. We'll meet again at 2:50. Okay? Good luck.
Okay, doctor.
Okay. Hopefully everyone already done. Okay. Are you write some name here? So number 1, find the total number of diagonals for a polygon of n sides if n equals to 6. Okay, Salirina, can you give me the answer? Share with your friend. Salirina ada tak? Salirina Lamiri.
Yes, doctor.
Okay, what is the number of diagonal for polygon of 6 sides?
My answer is 9.
Okay, good. 9. Okay, well done. Okay, for B, for a polygon of 8 sides, Amirul Haziq, share your answer, please.
My answer is 20.
20. Good. Okay, okay. Last for question 1, Jurina.
My answer is 35.
35. Okay. So I hope everyone got the same answer. Is there anyone that doesn't get the same answer and have any question about question 1? No, because I think like this is quite direct forward. To find the total number of diagonal, you just use this equation here, just plug in the value of n, then you will get the value of t. Okay, so question 2. Find the sum of the measure of the interior angles of a polygon of n sides. So this one, when you talk about sum of the measures, we just use this equation in the theorem 2.2.2, this formula here. So 2a's, Daphne.
My answer is 135.
135. Hmm.
Yes, doctor.
Sekejap, ke saya yang buat salah? You guna formula yang mana? Yang S kan? Daphne.
Yes, doctor.
So if n equals to 8, then if you put n equals to 8 here, so 8 minus 2 is equals to 6, and then times 180 degrees, you got, I got 1080.
Yes, madam.
Me too. Yes, Dr. Sam.
I think maybe tersilap kot Daphne. Sini you dapat 100, dapat 35 yang tadi. So the correct answer is 180 degrees. Okay? Daphne,
Okay, doctor.
okay tak? Ke tak faham tak? Faham tak macam mana boleh dapat 1080?
Paham, doctor.
Okay. Tak apa, tersilap sikit-sikit tak apa.
Okay.
Okay. Thank you. Okay, next Gonzales.
I got 360 degrees.
Say again, sorry.
360.
360, good. Thank you. Okay, C, Akila.
1440.
Okay, good. 1440. Okay, I hope everyone got the same answer. If you have any confusion anywhere, you can just let me know. Okay, number 3, find the number of sides for a regular polygon whose measure of each interior angle is this list here. So this question are looking for number of sides given the measures of each interior angle. So this one we are using corollary 2.2.1 where we get the value of I, we need to find the value of n. So when when I equals to 108 degrees, Norna Shafina, what is the value of n?
I got 5.
Yes, 5. Good. Okay. B, when I equals to 168 degrees, Naim?
I got 50.
Say again?
50.
50, 50?
30.
30, okay. Thank you. Very good. Murshid, when I equals to 150?
12.
12. Okay. And then last one, Fatimi. Value of n equals to
10.
10. Okay. Okay, it's quite easy, this one. So, congratulations, everyone. So, next, we're going to move to a new subtopic, which is symmetry and transformations. Okay. Okay. In this part, I think like we already covered most of the thing that you're gonna learn here. We already learned it during high school, so but we're just gonna recap. So symmetry. What is the definition of symmetry? So we say a figure has symmetry with respect to a line L if for every point X on the figure, there is a second point Y on the figure for which L is the perpendicular bisector of XY. So for example, you have a line segment of XY and X is symmetry to Y when there's a line L which is the perpendicular bisector of X and Y. So let's consider this example here. So you have figure A, B, C, D here, rectangle A, B, C, D, and it has a vertical symmetry with respect to line L. So point A and point B, point L is the, what we call the bisector for these two lines. This is the one that have been mentioned here about X and Y, perpendicular bisector. L is the perpendicular bisector and also C and D. And rectangle PQRS here has a horizontal symmetry with respect to line M. So if you draw any line here, you can have another line here where M is the perpendicular bisector of these two, the 2 points. Okay. A figure has symmetry with respect to point P if for every point M on the figure, there is a second point N on the figure for which point P is the midpoint. So this definition and the previous definition is just the same, but the previous definition, they are the figure is with respect to a line, but this one is with respect to point. Okay, so however, you can see the different in the next example. Okay, in other words, we can say that the point symmetry, that before is line symmetry and this one is point symmetry, when every part has a matching part and the same distance from the central point, but in the opposite direction. So note that a polygon having a point symmetry will look the same upside down. So let's look for example. So this one is for the line symmetry. So we have line L and line M here that will like kind of divide where the figure to have a symmetry. When you look on the right side, it will be the same on the left side. And when you look the top side, it will be the same and at the bottom side. But for the point one, it's quite different here. So you can see in the figure 2.4.1. So if you put point P here for rectangle A, B, C, D, so have a rectangle ABCD is also said to have symmetry with respect to a point. As shown, point P here is determined by the intersection of the diagonals of rectangle of ABCD. So if you consider point D here, then you will have B as the point symmetry for D. Same goes here. When you have M over here, you can have another point that in the other direction of the point P with same measures of a line. So note that a figure has symmetry with respect to point P if for every point M on the figure. So you can move point M in any point in the rectangle ABCD. There's a second point N on the figure for which point P is the midpoint of MN. Okay, so if example you have point M, but then the second point, which is the symmetry for M with respect to point P, let's say the point N is outside the rectangle, it's not on the rectangle ABCD, then we can say that point P is not the point symmetry. Let's say, for example, you move point P here. Point P is not here, but over here. Just let me show you. Okay, suppose this is point E. So let's say you move point P over here, not over here anymore. So if you have point M here, when you want to draw the second point, which is the symmetric, the point that is symmetry with M with respect to a new point P here. So let's see, this one is P dash here. Then you obviously won't get the second point, which is N, on the rectangle of ABCD. The point will be much more further here, isn't it? So this point P dash here is not a point symmetry for the rectangle ABCD. Okay. Okay. So look at all these 5 polygons that we have here. We have isosceles triangle, square, rhombus, regular pentagon, and regular hexagon. We know that which figure have point symmetry. Only the square, rhombus, and the regular hexagon have point symmetry. And in the regular pentagon, consider the centrally located point P and note that AP equals to PM. So square, if you put a point, let's say point P in the middle, so any point on the square will have a second point on the square as well. Same goes to rhombus. If you put one point, let's consider point M as the first point and point N as the second point. So if you have point M over here, you will have N here, or if you move, you will always have the second point on the rhombus. If you have point symmetry over here. Okay, same goes to regular hexagon. However, for regular pentagon, if you put point P here, the symmetry point over here, the point symmetry over here, you're gonna see that from point M, the second point, point N, will be here, and the length won't be the same. Okay, same goes if you put a point symmetry on a isosceles triangle. Let's try. Oops. Okay, let's say this is we thought to be the middle of the isosceles triangle, but this one is not a point symmetry. But if, for example, this is point M, when you reflect, when you want to find the second point, it won't land on the side of isosceles triangle. It will land like inside the isosceles triangle. Okay, but if you move here to say that you're gonna have point M here, have a same have length, for example 2, and then you have length 2 here for N. You have one line here, but then when you try to draw, when you move the point M to this side, then your N will be outside from the isosceles triangle. So that's why isosceles triangle doesn't have point symmetry. Okay. Okay, let's look at this figure below. So figure below has point symmetry O. Since we have this one look like letter S. Okay, so if you have point M over here, the second point will be point N over here, and you can see that it will have the same length from point 0 here, okay, and 0 will be the midpoint between this M and N. Same goes if you move the M over here, N over here, then you will have O as the midpoint of between M and N. If you want to try to see, like this one, for example, this is your M, okay, your N also going to be over here, somewhere in this part. And you're gonna, when you try to look at the length between this point to 0 to O, point O, and then point O to this point, you will have the same length as well. It's congruent. So figure below has point symmetry. This figure has point symmetry at O. Okay. Okay. This is symmetry. Next is transformation. Okay, when we talk about transformation, it's preserve the shape and size of the given figure. Whether transformation preserve length and angle measures thus leads to a second figure that is congruent to the given figure. Normally when transform, we have like some rules, which is, okay, let's look. The types of isometric transformation, which is slide or translation, reflection, and also rotation. Okay, so these three types will define what transformation you are doing for the figure. Okay, let's look for example for slide or translation. Every point of the original figure is associated with a second point by locating it through a movement. So macam kita slide kan, ada movement of a fixed length. For example, we slide or move for like 5 points, okay, then all the points gonna move 5 points from the original one. Okay, and the direction also need to be the same. Slide simply mean moving. Okay, so for example here we have this the original one. So when we slide or we do the transformation for this figure, we this one move to here, here, and here. So we will have the second figures, which is have the same length and also direction from the first one. Okay, let's consider the following diagram, X, Y, and Z. When we want to slide to the right, we can form R, S, T here. So when we want to write, the corresponding vertices is given by X, R, Y, T, and Z, S. So we didn't add this symbol here. Okay. Okay, the third one, suppose A slide to A prime over here, complete the slide of the figure below. So I did try this one. So this is a rough drawing. When we try, we like sliding, like move from here to here, we can have A to A prime here, B to B prime here. You can draw the line as well. Yeah. Okay, B here, B here, C here, D here, all the same length. As you can see, I just copy and paste here. I don't have to, obviously my figure is a little bit not exact as what it should be, but you can clearly see here it's like kind of sliding or move towards like to the right kan. Okay, if you want to write the transformation, then this is how to show that from A to A prime, okay, and so on. Okay, now the second part is reflection. So every point on the original figure is reflected across a line in such a way as to make the given line a line of symmetry. So when you talk about reflection, we always we can easily link to mirror. Okay, So reflection, mirror. So each pair of corresponding points will lie on the opposite side of the line. It's quite different from the slide, because if the slide point B here on the left side, and when you draw the transformation of this figure here, point B, B prime will be on the left side as well. But reflection is going to be on the opposite side. Okay, but note that it must be at the same distance. Okay, in other words, a reflection is a flip over a line. So like for example, you draw in one paper and then you fold it, and then let's say that the drawing like transferred to the other side of the paper. So that is how reflection is. And the line of refraction may be vertical or horizontal or oblique or slanted line. So it is a straight line, but it can be vertical, horizontal, or slanted. Slanted toward the left or towards the right. So for example, here you have a horizontal reflection. So M and P here, when you reflect, M will be from the left side of the figure, will be on the right side of the figure. The second figure is a G over here. N is H, P is K. Okay. The length between the two figure is the same, but it's not what we call the side of the polygon for this the original one and the reflect one is the same. It's just the side will be different, okay, because it's reflecting. And now if we have a vertical reflection, A, B, C, A will become X, from top become the bottom one, B will become Y, and C becomes Z. Okay, so I think you can see the difference between reflection and also slide or moving. This one is slanted. This figure doesn't really look slanted, but you assume lah, line M ini is quite slanted. So A, B, C, A will become P, B will become O, C will become R over here. Okay. Okay, next is rotation. When we talk about rotation, you can assume something like normally in our daily life we look at the clock, it's rotate, but for a clock it's rotate clockwise lah, obviously. But in geometry, when we talk about rotation, it can rotate towards the right, which is a clockwise, or towards the left, which is anti-clockwise. So every point of the given figure leads to a point or its image by rotation about a given point through a prescribed angle measure. Okay, to do a rotation, the question will give you how many degrees to rotate the original figure to the image. Okay, for example, this one here, this one is the original one, and normally in the question they're going to supply its which point as the base point. For example, here this is the base point, and towards how many angle, and to draw it from the point to the point on the figure, and we will need to draw the second point by moving towards the angle listed in the question to get the reflected, the rotated point. Okay, the transform points. Okay, so this point here have been rotated to this point here, this point here have been rotated to this point here, and this point here has been rotated to this point here. All these 3 points have been transformed based on the original or main point here, and also the same angle. Okay. Okay, that's all about the transformation. So we have 3 kind of transformation. We have slide of move or moving, and then we have reflection, and the last one we have rotation. Okay, this is the third one. I think this is the last one for today. Okay, before this we already learned about 2-column proof, and we already learned about formal proof. So when we talk about 2-column proof, normally we were given the question like if what is the first statement, and then prove the second statement. Okay, so we have if and then prove the second statement. For example, if we refer to the slide that you can see now, let's say the first statement as P and the second statement is Q. So to do the two column